Welcome to Safety Lab. This is Chemical Health and Safety, an introduction to chemical properties. My name is Emily Reiter, and I'm the laboratory coordinator for chemistry and biochemistry. We sometimes call this experiment the Unsafety Lab, and that's because we're going to show you some potentially hazardous properties of chemicals. And more importantly, we're going to show you how to keep yourself safe when you are doing lab experiments or laboratory activities. Chemistry is the study of matter and the interactions or reactions with other matter and energy. So this lab session is designed to introduce you to some of these properties and some of the potential hazards that you're going to see when handling materials. Some chemicals provide different dangers depending on how you're exposed to them. If you think about water, water is necessary for life, and presumably you drink a certain amount of water every day. But if you were to inhale water, that could kill you. So the dose and the type of exposure is important. There are 4 main routes of exposure to hazardous materials in the chemistry lab and in real life. You could inhale or breathe in materials. The most obvious one is vapors or gases, but you could also inhale solids or liquids, and if these are dangerous, they can cause harm to you. So to avoid inhaling potentially hazardous materials, in a chemistry lab, we may have you use a chemical fume hood, and we'll show you what one of those is. We may have you work in a ventilated space, or we may have you work underneath a fume hood that's on a stove or a cooking appliance. Or we might have you do this outside. Absorption is another way that you can be exposed to hazardous materials. This is also known as skin contact. So if you set your hand down in something, or if you spill something on your skin, it can absorb through your skin. We may have you wear gloves or an apron or something to prevent skin exposure in that way. You can ingest hazardous materials, which means eat or drink these materials. Obviously, you're not going to eat or drink while you're handling potentially hazardous materials, but something else that you want to think about is you shouldn't be chewing gum, you shouldn't chew your fingernails, you don't want to be touching your face, because this is another way that you could ingest materials without really thinking about it. And finally, there's something called injection. Now, obviously, we're not going to have you pick up a syringe and inject something into you, but if you have cuts on your hand or breaks in your skin, if you have a rash or a scrape, that can provide access for hazardous materials to bypass your skin barrier and get directly into you. So again, you're going to want to wear safety gloves or an impervious apron, or make sure that you get this off of you right away if you do have breaks in your skin. There's 2 main classes of hazard that you're going to see in a chemistry lab or in other science courses. We have physical hazards, and these include things that are flammable or combustible, things that are explosive. We also include corrosive materials like acids and bases in physical hazards. And then we also have chemical hazards. Chemical hazards include toxins, irritants, and carcinogens in the worst case scenario. So we have physical hazards that are classified as having the following hazardous properties. Things that are flammable or explosive could catch fire or could explode under certain circumstances. Things that are unstable or reactive, maybe things like fireworks. You would consider those to be unstable or reactive. They produce a large amount of energy when they react with another type of material or in certain chemical reactions. We also have things that are corrosives or contact hazards, and the most common examples of these are acids and bases. We're going to see some of these throughout the semester, and you may see some of these in your real life, in the kitchen, in the garage, in other sciences. Things that are health hazards are things that pose a potential hazard to your health, obviously. You may have a single exposure that could be a hazard, or it may take repeated doses to cause a hazard. These things range from things that may be minor irritants, which can cause just a burn or abrasion on your skin. These could be things that are toxic, or these things could be sensitizers or carcinogens. Again, you're not going to see much of this throughout the course of general chemistry, but we want you to be aware that this could be a concern in science lab. We've told you about all of these horrible hazards. Now, how are you going to protect yourself? You're going to follow the safety rules whenever you're in lab or whenever you're doing a science activity. These rules have been developed to minimize your personal risk from laboratory activities. You're going to wear safety glasses or goggles, and we'll show you what those look like in just a couple minutes. Before you come to lab, you need to make sure that you've read through the procedure. You need to make sure that you know what each step is going to do, and you need to make sure that you understand it before you begin. If the procedure calls for gloves or tells you that you need to have extra ventilation, then please be sure that you do this. Work carefully and pay attention to what you and what others in the room are doing. If you show up and you're really tired, if you're distracted, obviously if you're under the influence of something, you're not going to be able to make good decisions, and you could be a risk to yourself or to other people. And finally, we want you to use your common sense. If it doesn't seem safe, stop and reread the procedure or double check with your instructor, with me, with your teaching assistant. Maybe there was a typo and your good common sense caught that. We want you to have fun. We want you to learn a lot during this lab session and for this semester. And most importantly, we want you to be safe. So we said that we call this the Unsafety Lab because we're going to do some demonstrations that show the potentially hazardous properties of some chemical reactions. You're not going to do anything like this during the semester. Your lab kit doesn't include these materials. But we do want you to be aware of what could happen if you just randomly mix things together, or worst case scenario, what could happen if you have things that are flammable or combustible or corrosive. So one of the first demonstrations that we're going to do will show you the effects of corrosive material, of acids and bases on a protein. We're going to simulate an eyeball. We're going to take an egg white and we're going to drip acid and base on it. And hopefully this will really emphasize to you why you need to wear safety glasses or goggles when you're handling materials, why you're doing chemistry lab, and how to protect yourself from this. So I'm going to put on my safety glasses. I'm going to put on an apron, and you should have one of these provided in your lab kit. And I'm also going to be wearing gloves, which will protect my hands from these corrosive materials. Okay. In this demonstration, we're going to show you the effect of both acids and bases on proteins. So essentially, we want to really demonstrate why we tell you you have to wear safety glasses or goggles when you're in lab. We're going to show you the effect of what would happen if you got corrosive material in your eye and why that would be such a bad thing. So I'm going to take an egg, and ideally, I'm going to be able to just get the egg white because this is most similar in chemical content to your eye. And I'm just going to get rid of my egg yolk. And I'm going to give you an applied safety lesson. You want to worry a little bit about getting raw egg all over things. You want to be careful anytime you're wearing gloves not to transfer material, but raw egg does potentially contain things like salmonella, so please be careful with how you get this around. So I have my simulated eyeball, and I'm going to take hydrochloric acid. You are going to use this several times throughout this semester. This is 6 molar hydrochloric acid. We'll talk about concentration in a couple of weeks. And I'm just going to drop a few drops of acid on one side of my giant eyeball. And you can see right away something is happening. If you have ever accidentally touched your eye while you've got acid on your hand, when you've got vinegar on your hand, you know that this burns. We're chemically burning your eyeball, or your egg white in this case. This is one form of corrosion. Things that are basic, things that are alkaline, also are corrosive. I have 6 molar sodium hydroxide, which is a base, and we're going to talk about acids and bases in a few weeks in lecture. I'm going to take a few drops of sodium hydroxide and also treat my simulated eyeball. Now what you might notice is where I put the acid, right away we see burning. It looks like cooked egg, it looks like scrambled egg. Where I put the base, we don't see anything happening right away. This tells us a little bit about the difference between how acids and bases react. With an acid, if you get it on you accidentally, you feel it almost immediately. You almost immediately start to feel it burning. This sodium hydroxide, this alkaline, this base that we dripped on the other side of the egg white, takes a little bit longer. So in some cases, basic substances can be more of a corrosive hazard than acid because you don't feel them right away. So it has a chance to sink down into your skin and cause a bigger burn over time. We're going to come back to this and take a look at it after a couple of minutes have elapsed, because we want you to see what would happen if you just let this burn go. So you may know what cooked egg white looks like. Right here, we have our cooked egg white. On this side is where we dripped our sodium hydroxide solution, our base solution. And if you look really carefully, you see a physical difference. It hasn't changed color, but it does feel very different. It's kind of formed a jelly. In either case, if this was your eye, there's probably no coming back. So wear your safety glasses or goggles whenever you're handling corrosive material. And if you even suspect that you've gotten anything on you, get over to the sink and start flushing right away. In this corrosion demo, we're going to show you the effect of a strong acid on sugar. Sugar contains carbon, hydrogen, and oxygens, much like a lot of different organic material. Your skin, your hair, your clothes, all are made primarily of carbons and hydrogens and oxygens. So this will kind of simulate the worst case scenario of what would happen if you were to get a strong acid on you. So I'm going to take just regular table sugar and pour it into a beaker. And then I'm going to use concentrated sulfuric acid, and because it's an acid, I'm going to make sure I'm wearing gloves. And I'm just going to pour some of this acid into our sugar. You can see that we started off with white sugar and a colorless acid. And we have our sugar starting to turn color. We're actually beginning to burn. We're chemically burning our organic material, our sugar solution. As we let this go on, it's getting darker and darker, and we're burning more and more of the sugar material. Which is one of the reasons that we tell you if you even think that you've gotten something on your hands, you should go over and flush your hand at the sink right away. If we let this continue to react, you're going to see that it really starts to produce a lot of heat. This is another side effect of a lot of corrosive material, especially sulfuric acid. It's producing so much heat that we are burning the sugar, just like a marshmallow in a bonfire. And we get this sort of singed corrosion tower of sugar material. This is producing so much heat that it's turning the liquid to a steam, to vapor. So if I were to put my hand close to this, I would feel heat just radiating off of it. What we want you to see in this demonstration is if you ever get corrosive material on you or your skin, get over to the sink and start flushing it with water right away. Dilute this, wash it away, get it off of you as fast as you can. In this demonstration, we're going to show the effect of a reactive material. Reactive materials sometimes are known as oxidizers, which means they contain chemical oxygens. So even in the absence of oxygen, these could still catch fire. We're using potassium permanganate, which is KMnO4. It has 4 equivalents of oxygen right here in the chemical formula. I'm going to take a few scoops of this material, which is sort of a grayish looking crystal. It looks very sandy. And I'm going to mix this with glycerol. Glycerol is also known as glycerin, and you can find this at the grocery store. If some fancy soaps are glycerin soaps. It's a component of triglycerides, of fatty acids that are found in animal fat. And it's going to be our carbon source in this experiment. All I'm going to do is mix a little bit of glycerin with our potassium permanganate. And when we let these two sit and react for a couple of minutes, they are going to spontaneously catch fire. Potassium compounds frequently burn purple or violet. When you look at fireworks and you see that purple flash in the sky, it's usually a potassium-containing compound, like potassium permanganate. So we want you to be aware of directions, and we want you to not randomly mix materials together. We're not going to send you many reactive chemicals in your lab kit, but it is important to follow directions, because if you mix the wrong things together, you could have something like this result. So in this demonstration, we're going to show you again the effect of a reactive material, an oxidizer, with a fuel source. We have potassium chlorate, which is KClO3. And again, potassium chlorate has chemical oxygens right in the chemical formula. So it will bring its own oxygen to the reaction. And this could occur in the absence of any oxygen. I'm going to mix a few scoops of potassium chlorate, and then I'm going to move this right out of the way. I'm going to mix it with sugar. Sugar is going to act as our fuel source. Sugar has carbons and hydrogens and oxygens, and you wouldn't really think about sugar being combustible, but we've shown you that we can burn it with acid. We can also burn it with an oxidizer. I'm going to mix these two together really well. And then we're going to show you that you can do chemistry with things other than chemistry glassware. We're going to use clay pigeons. We're going to use a stack of 2 clay pigeons. And we're going to use these because they crack nicely. This is going to produce so much heat that it's probably going to crack. And they're very inexpensive. And they're a little easier to clean up than broken glassware. The last thing I'm going to do is make a little bit of a well. So I've mixed an oxidizer and a fuel source together, and if we let these sit together long enough, they would react. But we're going to be a little impatient, and we're going to add a couple drops of acid, which will act as a catalyst for this reaction. Again, I'm using an acid, so I need to make sure I'm wearing gloves. I'm going to put a couple drops of acid in the back, right here in the center, and then I'm going to step to the side. So So again, we want you to see that you should not randomly mix things together in lab or in your garage or in the kitchen without knowing what the properties of these materials are. In this flammable demonstration, we want to show you that you don't have to have an open flame or an electronic spark to make something catch fire. We're going to use a solvent called carbon disulfide. We don't use carbon disulfide very often in real life or in science anymore because it's a somewhat toxic substance, but it's extremely volatile and extremely flammable. It's very similar to gasoline in that respect. I'm going to pour a small amount of carbon disulfide into this crucible. And we'll give it just a minute to build up some vapors. I'm also going to take my gloves off because I don't want my gloves to catch fire. The next thing I'm going to do is take a match, just an average match. I'm going to light it, I'm going to blow it out, and then I'll wave it in the vapors above this dish and see if we can get it to catch fire. So all I did was wave a heat source above the vapors in this dish and they caught fire. So this is also something to think about whenever you're handling flammable materials. Try to keep any other source of heat away from this. Keep this away from the stove, keep this solvent away from sunlight, keep this obviously away from open flame. In this demonstration, we're going to show you the effect of a toxic gas. I'm going to take a piece of copper. Literally, I'm going to take a copper penny, and I'm going to put it inside this beaker. I'm then going to dissolve the copper with concentrated nitric acid. You're not going to do this in chemistry lab this semester, but if you do have metals that come in contact with acids, it is very important to know that you can produce toxic fumes and vapors. So this is nitric acid. We're going to talk about acids in a couple of weeks in lecture. And all I'm going to do is put about 20 drops of acid on this copper inside this glass beaker. And I want you to practice your chemical observations and see what's happening. The copper is reacting away. It's dissolving in this concentrated acid. And it's dissolving so enthusiastically you can see some bubbles forming. And more importantly, you can see this really nasty gas that's given off. This is NO2, nitrogen dioxide, and this is an extremely toxic gas. We're doing this demonstration inside the chemical fume hood. You're not going to have this at your home or your workspace, so we're not going to do anything like this at home. But there are times when ventilation is important, and we're going to make sure that you understand why we need to do this in a ventilated space. This reaction is going to continue for a couple of minutes until much of the copper has dissolved away and until no more red-brown NO2 gas is given off. This demonstration is going to show you an invisible gas. Sometimes toxic gases don't look toxic. Sometimes you don't see anything at all. In this case, we would be able to smell it, but because it's so toxic, we're going to do this inside the chemical fume hood. The first solution that I'm going to take is sodium sulfide solution. And we may be using this later on during this semester. I'm just going to put a few drops in the bottom of this beaker. And then the next compound that I'm going to add is hydrochloric acid, which we're using a few times during these demonstrations and which you're going to use this semester. When I drip in hydrochloric acid, you may not see anything. You might see this solution gets a little cloudy looking, but nothing else happens, and certainly no creepy looking vapors start to come out. But we are generating hydrogen sulfide gas, which is really toxic. It turns out that there's ways to observe toxic properties without having to directly put ourselves in harm's way. This indicator paper is called lead acetate paper, And when it comes in contact with hydrogen sulfide gas, it turns dark color. So the more gas that's present, the darker this paper begins to turn. In really low concentrations, you may have smelled sodium sulfide if you have ever smelled rotten eggs, or if you've ever been near a septic system or an outhouse. One of the odors that you smell is sodium sulfide. However, sodium sulfide is approximately as hazardous as cyanide gas. Our noses aren't very calibrated, so we can't tell how much is present. So sometimes we have to use other methods to directly detect whether or not a gas is produced, so that we don't have to rely on our noses. So sometimes flammable reactions happen so fast that they put pressure on their surroundings. This is the technical definition of an explosion. In this Nalgene bottle, I have a small amount of ethanol. This is considered to be a flammable solvent, and it produces vapors that can catch fire in the right circumstance. I'm going to take a Tesla coil, which is an electricity generator that you may have seen if you've ever taken a physics lab. We're going to take the Tesla coil and touch one of these metal screws. When that happens, an arc of electricity is going to jump across to the other screw, and it's going to ignite the vapors inside this alcohol cannon. And when that happens, it's going to burn so fast that the cork is going to come flying off. So I'm going to turn the electricity generator on, and we're going to cause a spark.